All right, so we are on chapter 5, and we're going to talk about chemical reactions. We're going to talk about all the things that occur, especially in our bodies, right? In order for us to take the food that we eat and convert that to chemical energy and do everything that we like to do on a normal basis, we need chemical reactions to make that happen. So we're going to explore in this chapter those chemical reactions. So anytime that we have a chemical reaction, we're going to have some energy associated with that. And so that first section is all about that kind of energy. Then we're going to talk about how quickly those reactions go. We'll talk about the different kinds of reactions in the rest of the chapter. Okay, so first we're going to talk about thermodynamics. And thermodynamics really is all about energy. So you know when you eat your food, right, you look on the back and you see your nutritional label, right? And it tells you how many calories your food contains, and it tells you the different types of food inside whatever you're eating, and then how much total fat, how much total carbohydrate, that kind of stuff. So it's the measure of the energy content of that food, and each specific food has a different energy content. So if we can understand how we can take that food and convert it to energy, and a lot of times, well, almost all the time, you have a heat change when that happens. So you have an energy change and you have a heat change. And so the combination of those two things is called thermodynamics, right? When we have our hamburger for lunch or whatever you really like to eat, like crawfish, I like crawfish. When you eat, your food molecules are broken down, and this happens pretty easily. You've got all kinds of stomach acid, right? You've got enzymes inside of your digestive system, and it all works to break down the food. And so if we look at how quickly that happens and how quickly we can now do work and things like that, that pace or rate of the chemical reactions is what's called reaction kinetics. So kinetics is like how quickly or slowly a reaction happens. So it's all about speed. All right. So we talked in way long time ago, right? In chapter 1, we defined energy as the capacity to do work, right? So when we talk about energy in this unit, I want you to think about, okay, what are you going to do with that energy? You're going to use it to do something. So whenever we have a chemical reaction, we're going to exchange energy. So you eat that hamburger, right? And the energy is stored inside the bonds of the food molecules, right? And then you're going to change it into a different substance, like ATP inside of the body. And then you can use that energy and do work. And your cells can contract, like muscle cells, things like that, right? And so it's all about the transfer of energy. So sometimes we have kinetic energy, sometimes we have potential energy. Remember, we kind of talked about that before. And so we're going to come back to that. And always remember, when we're talking about these chemical reactions, that we write our chemical equations in a particular way. We always put the reactants, and then we have a yield sign, and that's the little arrow. And so yield tells us that we're making something, so it yields our products. So always remember, reactants going to products. So when we talk about any given reaction, right, one thing that we talk about is that reaction endothermic or is that reaction exothermic? And so it's important to understand what these terms mean. So if a reaction is giving off heat, if heat is produced, it is an exothermic reaction. Exo meaning out and thermic meaning heat. So heat flows out of the reaction. So if I look at, here's an example equation right here. Where's my heat? If heat is flowing out, that means it is being produced in the reaction. And so heat here is a product, right? Remember we said things over here are reactants, things over here are products. Well, heat's an example of a product. So you'll see this in hot hands. I don't know, we're down here in Louisiana, we don't need hot hands. I'll tell you, when I was up in Iowa, and we would go to the football games, and it was November, December. I mean, it was cold. It was cold. I had like hot hands. I had the hot hands in my shoes. I mean, it was freezing. So if you've ever used those, right, you know that you have to like pop the little metal thing on the inside to activate the reaction, to make the reaction go, right? The same thing is used in medicine, actually. And they do this for little babies, right? You know, in order to take blood from little babies, they usually take it from the heel of their foot. And so what they do is they put, it doesn't get as hot as a hot hand, but it gets warm. And so they put it on the heel of their foot, and that extra heat makes that part of the skin, makes the blood vessels kind of dilate. So it helps to pool the blood there before they have to actually do the stick. So they call that the infant heel warmer in order to get a little extra blood. All right, let's see. Then we have reactions that actually absorb heat, right? And these are called endothermic reactions. So in an endothermic reaction, endo meaning in, and then thermic meaning heat. So heat is required to make it go. So in this case, heat here is a reactant, right? So everything over here is a reactant, and everything over here is a product. And so this is an example of this is an instant cold pack, right? If you, in these cold packs, you have two parts. The first part is water, and then the second part you can have different substances, but a lot of times it's ammonium nitrate. That's what this is, ammonium nitrate. And what you do is you break it, right? And so that actually bursts the water, the membrane that separates the water from the ammonium nitrate. And when the two mix, right, the ammonium nitrate goes from a solid into a dissolved form, and a dissolved form means aqueous. So if you're ever looking at these equations and you see all these abbreviations behind, right? So let's talk about what these abbreviations are. If you have S, that's telling you, see if I can, maybe I need to move my picture down so y'all can see. Okay, so if you have S, that's telling you have a solid. And a lot of times, well, all the time, when it's in a chemical reaction, we put it in parentheses. So it tells us just the state of matter. So state of matter. Solid, liquid, and then you have gas, right? And then you'll also see AQ. AQ means that you have dissolved it in water. There's a difference between liquid and aqueous. Liquid, like if you take a metal and you melt it, you're going from a solid to a liquid. But if you take salt, NaCl, right, and you add water to it, what's going to happen is you're going to dissolve the NaCl. So it was a solid to start with, but then you're going to make aqueous NaCl, AQ, which means that you really have sodium ions and chlorine ions and water, right? But that's a side note. Okay, let me erase that. But you have aqueous, and aqueous means dissolved in water. Okay, so make sure you know the little abbreviations behind it, and that'll help you out. Okay, so when we look at any given reaction, there are a couple of different parameters that we need to think about when we're looking at our reactions. And one of them is the exchange of heat energy. So like we have different forms of energy, and heat is a form of energy. And so we call this scientifically enthalpy. There's going to be another word that's going to sound like enthalpy, but the way that you remember this is enthalpy has an H in it, and so we call this delta H, okay? And H stands for heat. So H, H, and H. So make sure you keep track of that, okay? So our change in heat energy is enthalpy, and we represent it as a delta H. So anytime you see a triangle, that's a delta symbol, and that delta is telling you change in. We use that all the time in science, all the time. It's just a really quick and easy way to say change in. So if we have an exothermic reaction, we are actually giving off heat, right? So you start out a reaction, you have your reactants going to products, right? And your reactants has a certain amount of heat. It has a certain amount of H, right? Of enthalpy. And when we go to the products, in order to get to the products, we are giving off heat. So if we have products that have a lower enthalpy, right? That means that our reactants had a high enthalpy, our products have a low enthalpy. It's telling us that delta H for this exothermic reaction is going to be a negative number. So this will give us delta H being negative. So that is an exothermic reaction, right? If you have an endothermic reaction, then it's going to be the opposite, right? Energy is absorbed. And so because you start out in your reactants, going to products, right? You started off at a low enthalpy. You had to absorb some of that heat in order to get to your products. So now your product has a higher H. So if we look at the change in the products to the reactants, what's our change going to be here? Our delta H is going to be positive. So anytime we look at this, in order to determine what my delta H is going to be, I'm always going to look at products minus reactants. Always, always, always products minus reactants. So if I have here a product that's a big number minus my reactants, which is a small number, I'm going to get a positive number. In my other one, right, I'm going to start out with my products. My products are a very small number, a lot of times negative, right? And then my reactants have a high value, right? So if you have a small number like 2 minus 4, what's your answer going to be? Your answer is going to be -2, right? So that's an example of something that is exothermic, where we have a negative delta H. All right, so remember, exothermic, heat released, and you get a negative delta H. And then endothermic, remember, heat is absorbed, and you get a positive delta H. The other thing that we measure in terms of a chemical reaction is called enthalpy. So enthalpy is, it's change in entropy, not enthalpy. Enthalpy is H. Oh, y'all, they messed this up. Okay, they messed this up. Is not enthalpy, is entropy. Entropy, right? Right here, entropy. Okay, so the measure of a change in randomness is entropy. So entropy, I want you to think about as disorder, right? Think about your bedroom. There are so many different ways that your bedroom can be a total wreck, right? But to pick it up, you have a limited number of permutations of what can be picked up. So if you look at the randomness in the system, right? If your room is a mess, it's super random. But if your room is picked up, it's not very random at all. So that's kind of entropy. So a messy room has lots of entropy. A clean room has not so much entropy. And so a lot of times we measure this in a chemical reaction. We see when we start or when we finish, what happens with the entropy. And so it's the same thing when we do this. If we want to know the change in entropy, we look at the entropy of the products minus the entropy of the reactants. It's the same basic setup. It's always, always, always going to be products minus reactants. So that's something you need to remember, products minus reactants. So a lot of times when we look at chemical reactions, right, things that are going to happen easily, we're going to have an increase in randomness. You think about if you ever heard this before, I'm asking you a question on a video. I think that's funny. The little saying, the universe tends towards disorder, that's randomness. So if you have a reaction where you have an increase in entropy, you're increasing the randomness, and that's a positive delta H. So if we increase randomness, we get a positive delta delta S. If we decrease randomness, we get a negative delta S. So let me give you some examples. A lot of times we talk about this in terms of state of matter changes. So if I have something that is a solid, let's think about water, right? What's going to happen with water? If I have solid water, that means I have ice. And if I put it out on my counter, what's going to happen to that ice? That ice is going to melt. When it goes from a solid into a liquid, that solid was pretty ordered, right? We have to have all those hydrogen bonds and they have this nice crystal structure. But when it melts, it goes to a liquid. Now all those particles can move around each other, right? So we have more randomness. So this is an increase in randomness or an increase in delta S. Now, if I leave that water out long enough, what's going to happen? Let's say I took an ice cube, I put it on a saucer, right? That ice cube will first melt into a liquid. Now I'm not going to touch it. What's going to happen to that water? The water is going to evaporate. So I actually go from a liquid to a gas. So when I change from a liquid to a gas, now I'm going from something that is liquid, you know, the particles are moving around, they're sort of close to one another, they're moving around. Now I go to a gas. A gas, the molecules are so spread out and they're going every which way, right? So which one's more disordered? A gas. So as we go from a solid liquid to gas, our disorder increases. So we have an increase in S, right? Now let's talk about decreasing randomness. If we decrease randomness, we have to go in the opposite direction, right? So let's start at the highest amount of disorder. We have a gas, right? If we cool that gas down, if we put that gas in like a refrigerator, right, what's going to happen is it's going to condense. It's going to condense into a liquid. Now you put that liquid, let's say in your freezer. So now I'm putting in more energy to make this happen. I get to a solid, right? All of this here happens spontaneously because you're going from low disorder to high disorder. So it happened spontaneously. It happened on its own. But going from a gas to a liquid to a solid, you're putting energy in. So it's not going to occur spontaneously. So when we decrease our randomness, we're going to have a decrease in our energy. Okay. All right. So a lot of times we talk about, you know, you have that hamburger, you eat that hamburger, you break that hamburger down. How much of that energy that you consumed in your hamburger is actually available for you to use to walk down the street? In order to figure that out, we use what's called Gibbs free energy, or delta G. And so in order to answer that question, we have to look at really three things. We need to look at heat, which is our enthalpy. We need to look at the change in randomness, or entropy, which is delta S. And we actually need to consider temperature, okay? So it doesn't say it in the text, but it is in the formula, and temperature. That's the three things. And so when you take these three things into account, then you figure out how much energy is present in the molecules that we can use to actually do work. And so we can use an equation to figure that out. Now, your book's not going to ask you to do calculations, but you do need to know the formula so that you understand the relationship between the different parts of the formula. So the formula says that Gibbs free energy is equal to our change in enthalpy minus temperature times our change in entropy. So that's not always an easy equation to remember. So I have this fun mnemonic device that I really like to use. So goldfish, and that stands for delta G. So goldfish, R tells you that you have an equal sign. Are horrible, delta H. Without tells you that it's going to be negative. Tartar sauce. temperature times delta S, which is entropy. So goldfish are horrible without tartar sauce. I'm sure they're also horrible with tartar sauce, but but that's our little mnemonic. So goldfish are horrible without tartar sauce. Gives you your Gibbs free energy equation. Okay. All right. So when we talked about something being exothermic or endothermic, all we were really talking about was heat, right? And so you can look at that and you can look at an equation and say, is it producing heat or is it releasing heat? But that's not really always important when we're thinking about our bodies. When we're thinking about our bodies, we want to know what's available and what's not. So is it going to occur very easily? Is it going to give off energy? Or is it going to require an input of energy to do? And so looking at delta G, whether it's positive or negative, we can determine if that equation, if that reaction is going to go or not. If it's going to go, it's called exergonic. It gives off energy. So, you know, when you break down food, right, you're going to gain energy from that. So that reaction, that breakdown gives off energy. Now, if I want to go build something like, you know, like my son who's 8, right, he's got to go really tall. I think he really is going to be tall. So if he grows really tall, that takes energy to grow. Like that boy can eat. It's unbelievable. And he's only 8. I'm terrified of my grocery bill in the future. So that would be something that requires energy, him growing. That's an endergonic reaction. So it requires energy to do. So when you look at an endergonic reaction, the free energy of our reactants is greater than the free energy of our products. So remember, it's always going to be reactants minus products, no matter what. Always, always, always reactants minus products. And so things that are endergonic are going to require energy, right? Things that are exergonic are going to give off energy. So exergonic reactions don't require an energy input. They occur spontaneously. So the breakdown of food a lot of times is very spontaneous, but creating new cells, not so much. So things that are spontaneous are going to continue to occur once they start, and they don't require an input of energy from the surroundings. So think about now, it doesn't always have to be your body, right? Think about rusting. Rusting is an example of a spontaneous process. It doesn't happen very quickly, but if you leave certain metals out, they're going to have a reaction with the oxygen in the air, and they're going to rust. So iron will react with oxygen to make iron oxide or rust. It's spontaneous. You don't have to do anything. You just sit back and wait, and it's going to happen. You do have to have patience because it's a slow reaction, but it's still spontaneous. It's still going to happen on its own. So your book has this relation to paddling a canoe, right? So if you're paddling, if you're going down, you know, you're going for a little boat ride and you're going downstream, you don't have to put energy in. You're kind of going with the stream, right? So that's a spontaneous reaction. But if you want to paddle your boat and you want to go against the current, you want to go upstream, then that's going to be a non-spontaneous reaction. And that's going to require your input of energy. And what energy are you inputting? For this example, you're paddling. So you're doing work in order to go upstream. So the canoe can only go upstream if the paddler is putting in energy. That's an example of a non-spontaneous process. Okay, so a lot of times when we talk about thermodynamics, we use a graphic, we use an image, and so it's pretty important to understand kind of what's going on in these pictures. So what's not written here, which should be, is this is energy, if I could spell. This is energy, okay? And then this is progress of the reaction. So when we think about progress of the reaction, remember, we're always going from reactants to products. So what this is telling me for an exergonic reaction is that my free energy of my reactants, I start out with a lot of free energy, right? And then when I go to my products, my free energy goes down. So if I subtract what I started out with, the maximum amount right here, this is what I started out with, minus what I end with, so this is my products. Whoa, not R, P. So my products minus my reactants, I'm going to get my delta G, right? So let's say, for example, your products are 25. If your reactant is 50, right? Well, it's more than double that, but it's a sort of good example, okay? So my products, right, were 25 minus my reactants, which are 50. What's my difference? Minus 25. So this is what happens in an exergonic reaction. I like to kind of think about this as hills that the reaction have to go through. So if I think about myself, I'm going to put, there's me, right? And I'm sitting on top of a hill and I'm riding a bike. I can't draw a bike. I don't even know how to draw a bike. There's my bike, right? It's a terrible bike. But I'm sitting at the top of this hill and I'm on my bike, right? How much energy am I going to have to input to get to the bottom of the hill? Not much, right? Because I'm at the top of the hill. So I can just kind of put my feet up on the bike and I'm going to race down the hill. So I'm going to have lots of free energy going down the hill, right? It's going to be easy. That's an exergonic reaction. Exergonic reactions are easy. They happen spontaneously, right? If you're sitting at the top of the hill and you are poised right on the edge, you can just go over and you slide right down that hill, or race down the hill, whatever you want to call it, right? But the opposite is an endergonic reaction. In an endergonic reaction, think about you sitting here. You're at the bottom of the hill. Oh no, you're at the bottom of the hill. And you're going to have to go all the way up in order to get to your product, get to your destination. Well, you're going to have to expend energy to do that. We're going to have to input some energy, right? You can't just sit there at the bottom of the hill and get to the top of the hill. In order to get to the top, we're going to have to work. We're going to have to put energy in order to get to the top, right? You're going to have to pedal your bicycle really, really hard in order to get to the top. If we are reactants, if we say our reactants here, this is our energy, is at 25 to start with, and it ends at 50, right? In order to get to that 50, we have to put 25 units of energy in, right? So if our product is 50 minus our reactant, which is 25, we get a positive 25. So we had to put in this much energy. And I'm just making up numbers just so that you can see the math actually happen, okay? But if you kind of think about it like a hill, you'll get the idea. So remember the difference between exergonic. Exergonic is going to be a negative delta G, and it's going to happen spontaneously. It's easy. Endergonic is going to end up with a positive delta G, and you're going to have to put work, you're going to put energy in to make it happen. Okay, so now let's think about our living system. Let's think about our body, right? So you have to think about cellular conditions, because this is what's making our bodies go. Everything that happens actually happens inside of cells. And so when we have a spontaneous change inside of a chemical reaction in our bodies, the free energy is going to decrease and the stability of our system increases. So if I'm going to eat look, she's being healthy. She's got salad. Oh, good for her. So let's say you're going to eat salad, right? Your digestion is going to break down that food. And during that breakdown, you're going to give off something. You're actually going to give off ATP. ATP is super, super important. Super important. You're going to give off this ATP. right? So you have an exergonic reaction that's digesting the food, digestion breaks it down, and it is going to make ATP. That ATP is energy. It's an energy storage molecule, and you can use that ATP in your body to drive all kinds of non-spontaneous reactions. So walking or climbing the stairs or anything like that is non-spontaneous. So to make it happen, you need an input of energy. Well, once you've eaten, now you made ATP, your body can use that ATP to fuel non-spontaneous reactions. And so you've probably heard in biology, I hope you have, that you know ATP is adenosine triphosphate. So it's got an adenosine molecule, and then tri meaning 3 phosphates. Okay, so we're gonna do our first little example problem. Classify the following as spontaneous or non-spontaneous. A chemical reaction with more energy in the products than the reactants. So remember, it is always products minus reactants. So if you have more energy in the products, so let's say 50 minus 25, right? I have something here that has more energy in the products than the reactants. What am I going to get? I'm going to get a positive number. So if I get a positive number, so this is, for example, delta G, if I get a positive number for delta G, what I can say is that chemical reaction is going to be non-spontaneous because I'm going to have to put in this much energy. So A is non-spontaneous, right? Okay. The oxidation of food by the body. So remember, this is what we were talking about. When you ingest food and food goes into your body, the overall breakdown of that food is going to produce energy for you, like to be used in muscle movement. So this is a spontaneous process. Spontaneous, right? Okay, a chemical reaction with a negative delta G. Well, we just said below that if you had a positive delta G, you were non-spontaneous. So if you have a negative delta G, this is a spontaneous reaction. And remember, spontaneous is equal to exergonic, whereas non-spontaneous is equal to endergonic. So these are some new vocabulary words. So I would definitely suggest doing some little flashcards and things like that for our new vocabulary. Okay, thermodynamics. Sometimes, most of the time, in order to get any reaction to go, they need a little push. So remember, we're talking about the hot hands, right? So how do you get the hot hands to work? You actually have a little metal disc, and you have to bend and pop the disc in order to expose the metal that's inside the disc to the solution that it's in. So that's the little push that it needs to get started. Or, but that's a good example. Okay, so what really happens, like why does that happen? Why do you have to pop the little metal? Well, inside of the solution, right, you have metal ions, and a lot of times they're sodium ions. Sodium, if you look in the periodic table, is going to create an ion that is positively charged. So it's a cation. And then usually you have another molecule that has a negative end. So you have your sodium that's positive, and then it's usually acetate, and acetate has a partial negative charge. And so that sodium has to get on the correct side of the acetate that's negative. Because remember, molecules can be polar. So one side of a molecule can be negative, one side can be positive. Well, if my sodium's positive, my sodium doesn't want to hit the positive end of my acetate. It'll just repel. What I want is for my acetate to be in the right orientation and for my sodium to hit it just right. So that's the little push. They need to collide with enough energy and in the correct orientation. That's the push. So we call that energy the activation energy. And so if we look, this is the same kind of graph that we saw before. Before we said, okay, this is the amount of energy in our reactants, right? And this is the amount of energy in our products. And that's true. We have this amount of energy in our reactants and we have that amount of energy in our products. But the path that it takes is not a straight shot down. You actually have to put in just a little bit of energy to make it go. So think about me sitting on that bicycle at the top of the hill. I'm sitting there, I'm at the top of the hill, I have a lot of this potential energy, but how am I going to actually get going to go down the hill? You know, somebody's going to have to give me a little push, or I'm going to have to pedal just a little bit in order to hit the slope and then slide down. So this is me pedaling just a little bit, and then, whoa, so I pedal just a little bit, and now you're on the very edge and you just put your feet up and you slide right down, right? So it's the same thing in a chemical reaction. You have to give it that little bit of push in order to make it happen. So the amount of push that you have to give, you look at however much energy you start out with in our reactants. So that's our reactants. Here's our products. Whoa. So you look at the amount of energy you start with as the reactants. And then you look at the maximum amount of energy that had to go in. And the difference between the two is called the activation energy. Right? So maybe you started here at 50, but you actually had to go up to 55 before, that's right there, right? Before you could coast down and get to a product that is at maybe 10, right? Okay, so let's look at our other example. Let's look at an endergonic reaction, right? An endergonic reaction starts out and it has a very low amount of energy. And when it ends, its products over here have a high amount of energy, right? That was our previous little diagram. So if I'm sitting here at the bottom of the hill, poor me, I'm sad, I'm sitting here at the bottom of the hill, and I need to get to the top of the hill, what am I gonna have to do? Am I just gonna pedal my bike a little bit? No, I'm gonna have to pedal the whole time in order to get all the way to the top of the hill, right? So the activation energy for me is from wherever I start to the maximum amount of energy. Oh my gosh, that's a lot of activation energy, right? Look at that. That's a huge amount of activation energy. So I have to put in a lot of energy to make an endergonic reaction go. You need a lot of energy, okay? That's why we have delta G, positive delta G for an endergonic reaction. But the activation energy for an endergonic reaction is really, really big, and the activation energy of an exergonic reaction is relatively small. And if you think about yourself on a bike, it'll work. Every time it'll work. Okay, so let's look at a sample problem, right? All right, which of the following diagrams has the following characteristics? An exergonic reaction. So I'm going to look at the two. And remember, exergonic means that you are going to release energy, right? So in which of these am I actually going to release energy? So you should have said diagram A is an exergonic reaction. I'm releasing energy. So that the energy of my reactants, right, is higher than the energy of my products. So I'm actually going to release this much energy. So from here to here, this is energy released, right? Okay, so then B, endergonic. Endergonic means that our reactants are going to have less energy than the products. So that's going to be my other figure, that's going to be B, right? Where our reactant started out low, and then we had to put energy in order to get to our products, okay? All right, C, delta G is negative. So look at our change in energy. Which one is going to give me a delta G that is negative? Well, if my reactants here are starting out at 50, you can always just put a number to it. And I'm going to end at 10, right? And I know it's always going to be products minus reactants. So delta G, right? Products minus reactants. What's my product? My product is 10. My reactant is 50. I'm going to get negative 40. So delta G is negative in figure A. What happens with figure B? Well, if figure B starts at 10 and ends at 50, so that's for A. For B, we're going to have delta G, same thing, products minus reactants. My products are going to be 50. My reactants are 10. What's my answer? My answer is 40, but it's positive 40. So be careful about that, positive 40. So delta G is positive will be B. Okay. All right. So thermodynamics. When we talk about energy inside of our food and things like that, right? We talk about calories. Remember the big C, calories? And we said that's what's on the back of the nutrition bottle. And so containers, whatever it is. So whenever we say that, we say, okay, we're going to eat this many calories. Now I'm going to go exercise. And I want to know how much of the calories I ate did I burn when I exercised? Well, did you get yourself a match out and burn yourself? No. So why do we call it burning calories? Well, we call it burning calories because it is a combustion reaction. So when we talk about a combustion reaction out in the environment, right, you have oxygen that's being reacted with whatever molecule it is, and it's producing fire, right, that we see. Well, inside of our bodies, we do have combustion reactions. They're just way smaller scale. So every single combustion reaction, whether it's inside or outside of the body, is where our oxygen is reacting with some other substance, and it's going to produce carbon dioxide, it's going to produce water, and it's going to produce energy. And so that's what we call combustion. And so when we look at the foods we eat, the starting material is different, right? You have carbohydrates, you have proteins, you have fats, and those different substances will react with with oxygen in different ways. And so you get different amount of energy out from those nutrients. So fats, right, will give you a lot of energy per gram, right? So this is in units of big C calories per gram. So fats are going to give you more energy per gram of food, right? That's why we try to limit the amount of fat in our diets. So if you want to know the total caloric count, the total caloric content for any dish, any food, anything you buy, right? You take the sum of all the calories, big C calories, present for each nutrient. And I'll show you how to do that. So here are just some examples of various different foods, right? And you can see that the different foods are all made up of some combination of either carbohydrates, proteins, or fats. And so you can end up having things that are very close to the same. So look, for example, here, the same total calories. Butter and corn have the same approximate total calories, 104 on 103. But they're made out of very different things. So butter, on one hand, is primarily fat, right? So all of your calories are coming from fat. If you look at corn, corn is mostly carbohydrate. So most of your calories are coming from carbohydrates. So each particular food has a combination of those three. And so we're going to look at how to do that in a math problem. So if you were given a nutrient label and said, okay, in one serving size, in this case, it's 2 tablespoons, what is the total amount of calories inside of what you are about to consume? So what you're going to do is you're going to look at the total, look at your little nutrition label, right? You look at total fat, you look at total carbs, and you look at, they just call it protein, but it's total protein. It's the same thing, right? So we said our fat had said 12 grams, our carbohydrate says 15, and our protein says 7. So you need to be able to convert and to say, okay, how many calories are in 1 gram of that fat. So you have to go to a table. So a table will be provided for you. So you know that if you have 12 grams of fat, well, here's my conversion, right? So there's 9. So you have 9 calories that equal to 1 gram of fat. So 9 calories are equal to 1 gram of fat. So you can use this conversion factor and do dimensional analysis. I want fat to cancel, so I'm going to put fat on the bottom. I'm going to put calories on the top. I get 108 calories from just the fat inside of that serving size. That's not the only thing in it. So I have to do the same thing for my carbs. I have to do the same thing for my protein. Once I get all 3, I'm going to add them up, and I get a total of 196 calories. But be careful, because you need to worry about significant figures. So if you look at your significant figures, your least significant values all have 1 significant figure. So you need to put your answer to the correct number of significant figures. So I want 1 significant figure. So how am I going to round 196 to 1 significant figure? 200 big C calories, okay? Because you can only have 1 significant figure, so the 9 makes the 1 round up to a 2, but don't forget your place value zeros. Okay. So a lot of times when you see foods, you'll see them marketed as low calorie, right? And so if you compare soft drinks, right? A regular soft drink has a lot more calories than a diet soft drink. Why? Well, most of the calories in your soft drink come from sugar. And so a lot of food manufacturers will use artificial sweeteners, which are molecules that are not sugar, and they're very unreactive in the body, but they taste sweet. So they give us the same feeling, but they don't have reactions inside of our bodies. And so they stay basically together, and they don't produce a lot of energy. Fats produce the highest amount of energy per gram, right? And so a lot of times manufacturers will do the same thing with fats that they do with sugars, and they'll manufacture things that have fat substitutes. So it still tastes like our normal, whatever it is that you're eating that's a high fat, but your body's not going to be able to break it down. And so that's your low fat alternative. So they use things like dextrans and celluloses and gums, right? And these are carbohydrate based instead of fat based. And so you end up with less energy when you eat them. Right? So here's an example. Calculate the number of calories present in a slice of pizza that contains 34 grams of carbs, 13 grams of protein, and 12 grams of fat. So let's do our carbs first, right? Our carbs, we said 34 grams. Okay, so if I come up to my top and I say, okay, I know I have 4 calories per gram. So be careful that you associate the right things with the right units. Okay, so I have 4 calories per gram. So that means I have 4 big C calories per 1 gram of carb. Okay, so my carbs cancel out, right? And so I get 136 calories. Then I'm going to do, what's the next one? Grams, protein. Oh my goodness. If I could write today. Protein. Okay, so I had 13 grams of protein. So I look up here and I say, okay, my protein is another 4 calories per 1 gram of protein. So that should give me 52 calories, big C calories. Then I need to look at my fat. So I'm told 12 grams of fat. And I know I have 9 calories per 1 gram of fat. My fat cancels. I should end up with 108 calories. So now I need to add up 136, 52, and 108. And when I total that up, I get 296 calories. But I said that's not the right number of significant figures. So I need to round that. So my 9 rounds my 2 up. So I'm going to get 300 calories. 300 calories. Okay. Is that? Yep, that's the end. We're going to go do some practice problems. Okay, so here we go. We're going to leave the first 2 to do in class, and then we're going to do the rest of the odd in this video. So give the sign for delta H if for the reactions in problem 5.3. Oh, but I got to go do 5.3. Okay, classify the following as exothermic or endothermic reactions. So A, when 2 solids are combined in a test tube, the test tube gets hot. So if the reaction gets hot, that's telling you that it is releasing energy. If it is releasing energy, it then must be exothermic. And for reaction B, a reaction must be heated for it to continue. That means we are putting energy in, and it is endothermic. All right, 5.5. Give the sign of the enthalpy, delta H is the enthalpy for the reactions that we just did, right? So when 2 solids are combined in a test tube, the test tube gets hot. So if you are releasing energy, if you are releasing heat, right? Then that's telling you that heat is a product, and that's telling you that your delta H must be negative. Negative, right? A reaction must be heated for it to continue. This is, on the other hand, telling you that your heat is going to be part of the reactant. And so you're going to actually have to put heat in order to make this reaction go. So in this case, delta H must be positive. Okay, so you just need to kind of work on those. 5.7. Here we go. Would the sign of delta S be positive or negative for the following changes? Now, before you answer this, I want you to think about what it means for delta S, for entropy. Okay, so if something is more random, that's telling you that you have an increase in the disorder. So delta S is going to be positive. If something is less random, that tells you that you have a decrease in your disorder. So delta S is going to be negative. If you can remember that, you'll be fine. So A, freezing water to form ice. Here's the trickiest part. You need to identify products and reactants. So make a normal reaction where you have a yield sign. So water freezing to form ice. What's my product? My product is my ice. And remember, ice, if we're going to make ice, right? And our water is freezing. So we have water is a liquid, and that liquid is turning into ice, which is a solid. So if we're going from a liquid to a solid, what's happening to our randomness? We're getting less random. So we have a negative delta S. A protein being formed from amino acids. Hold on. So if you think about this, what's happening? The protein is being formed. If whatever's being formed, this is going to be your product. From amino acid is going to be your reactants. And so you don't have to have a real chemical equation for this. All you have to think about is my reactants are going to be many, right, amino acids. If I have many, many, many amino acids that are going to make one protein, what's happening to my disorder? Well, I'm getting more organized. I went from many little things to one big thing, so I became less random. So then I'm going to have a negative delta S. Look at the last one, our digestion of a meal. Think about what's happening here. right? Let's think about, I'm gonna eat a slice of bread. Hold on, y'all. If we're digesting food, you're going from one slice of bread, let's just say, right, into all of these bits and pieces, right? So you're going from one slice of bread to many, we'll just say components, right? So you're breaking it down. So you're going from one thing that's big into many smaller pieces. So anytime you're going from one thing to many things, right, you're becoming more random. If you are more random, that means you have a positive delta S. Okay. All right, let's go to 5.9. Classify the following as spontaneous or non-spontaneous. Remember, spontaneous occurs without any extra help. A hot bowl of oatmeal cooling on the table. You don't have to do anything, so this one is spontaneous. A chemical reaction that gives off free energy. If a chemical reaction is giving off energy, you don't need to do anything to make it happen. It's doing it on its own. So this one is also spontaneous. All right. Now we're going to do a little bit of calculation. All right. We need to calculate the number of calories present in a chocolate chip cookie. All right. Our chocolate chip cookie, we are told, has 17 grams of carbs. It has 1 gram of protein, and it has 7 grams of fat. So what you need to do is you need to convert from carbs, protein, or fat into calories. So you're going to use this table right here. So my 17 grams of carbs, I know in carbohydrates, there are 4 calories per gram. So in 1 gram of carb, I have 4 calories. Protein, on the other hand, protein, I have another 4 calories in 1 gram of protein. And then in fat, remember fat's a little different, it has 9 calories. You don't have to remember those values. You don't. Grams of fat. So my fat cancels with my grams, my proteins cancel with my grams, my carbs cancel with my grams. So I do my math. So 17 times 4, I should get 68 calories. 1 times 4 is 4, so that's 4 calories. And then 7 times 9 is 63, so I should get 63 calories. So now I'm going to add these up. I'm going to say 63 plus 4 plus 68. I should get 135 calories. R-I-E-S. But remember significant figures, 135, you don't have 3 significant figures. You really only have 1. A lot of times they'll also list it as 2, but technically it's only 1. So I'm going to say that's 100 calories, right? Okay. And that is the end. Yep, that's the end of our problems.